Hello everyone. I hope that everything works and the stream works. Actually, yeah. I know that I need to start sharing my screen. Give me a second. And I also need to check. Yes, it's started. And the screen. If I forgot to share it, that wouldn't be the first time. But now we are here. Will you show me myself? No? No, Riverside doesn't want to show me the video that I'm recording, which is fine. Let's just set the timer. Do you see this problem? I see this problem. It's another hard problem, and I'm pretty intimidated by it because of this rating. My rating is around 2100, 2200, so this problem will be a stretch for me. If I succeed, that will be exciting. If I don't, that will be expected. Let's just try to do the best I can. There are n items, each belonging to 0 or 1 of m groups. Okay, group I is the group which the ith item belongs to, and it's equal to -1 if the ith item belongs to no group. Okay, so group is a list of integers. The items in the group are 0 index, fine. A group can have no item belonging to it, okay. Return a sorted list of the items such that the items that belong to the same group are next to each other in the sorted list. There are n items each belonging to 0 or 1 is the group that each ith item belongs to. Okay. There are some relations between these items where before items, which is also a list of integers, is a list containing all the items that should come before the ith term in the sorted array. Okay, we are returning a list of integers, right? And n items. I'm not sure if we are getting n as input or we just have to measure it from the sizes of the list. Let's see. Okay, we are giving n and m. Oh, interesting. So m is actually this before items is a list containing. Okay, so this will be a list of integers. Fine. And what I'm currently not getting is that, do we have basically n items that are from 0 to n-1? And we should also sort those inside the groups. And what is m? What is m? Of one of m groups. Okay, I get it now. So we have n items, m groups. I haven't seen the tests yet, so let me just make some assumptions about how this whole thing works. So group will be, okay, let's say there is an item that belongs to no group. So this is -1 item belongs to no group, then the second item belongs to group 1, another group 1, and another in group 2, another group 2. Okay, so then we are saying that, let's say, before items, it should come before the ith items. Give me a second. Sorry, I was just telling something to my family. Before items. So what should I say? Let's say we have, okay, for the first item, let's say item 3 should be before it. Then for the second item, let's say item 0, 1, 2, 3, 4. Okay, 4 should be before it. And then we don't create any more constraints for now. So clearly the number of groups is 2 and the number of items is 5. And what should we return here? Should we return something like, okay, so we have a requirement that before this item that belongs to no group, we should have item number 3, which is this item. So group 2 should go all before this item 1. And we also have that this item from group 1 should go also after group 2. So the whole group 2 should come before group 1, and the whole group 2 should go before group -1. But between -1 and 1, we don't have any specific ordering. So that would mean that it works like there are two options. First option is we do 3, 4, for example, and then 1, 2, and then 0. That's one option. And second option is 3, 4, 0, 1, 2. Then what is also not clear, whether we should sort those items inside those groups. Return a sorted list of the items such that does it mean that this is not a sorted list? Because this is not a sorted list, but it's sorted in the way that is required to be sorted. Let's see. Okay, so yes, this is a sorted list. We're returning it correctly. Let's now see example. Oh, we have a nice spreadsheet. Let's check. So these items belong to no group, and we know that before this item we should see 6, and before this we should see 5. Before this we should see 6, and before this we should see 3 and 6. So it means that item 4 needs to go one of the six needs to go. It's just one of the options I see. So basically 4 before 4 we need to have 4, 6, and 3. And okay, we also have groups, right? We have group 1. In my test I didn't start with 0. In our groups I should have started with 0. So maybe let me just do that right now to correct my mistake. And here we see 6 and 3 that are coming before this item 4, then the 4 itself, and then the only other constraint that we have is that item 5 should go before item 2, so 2 and 5. And now the groups themselves, right? So 6, 4, and 3 should be together. Oh, but there is also, okay, so the challenge here, let me just mention it. Challenge that before items needs to be used both for inter and intra group relation, like sorting. So what I'm trying to say is that elements of one group, let's see this element. So here, for example, we can say that 0, 0, right? They're belonging to the same group. But let's say that the last element, the previous last element, should go after the last element, so 5 here. And that would make this ordering incorrect and this ordering incorrect. The only ordering that would be correct is 2, oh no, sorry, 3 and 4, we are considering these two. So we need to sort those 3 and again here 4 and 3. Okay, so this gives me an idea about what we need to do, but let's see if we can actually do that. Solution. Okay. First of all, we have mapping, clear mapping between an item and the group. So it's already kind of like a dictionary. So then we can figure out whether it creates a graph for us. So there is some like topological ordering here, where we have to create ordering between graphs. Oh, sorry, ordering between items, but each such ordering is basically a directed edge in a graph. So, for example, here we will have a directed edge between, let's also say that we need to have group level ordering, and maybe, okay, maybe we can process these independently, two things. So one thing will be group level ordering. We can sort the groups between themselves. And then we can also have an item level ordering inside the group. So first of all, we need to figure out if we have cycles in the bigger graph. That is group level graph. And then we need to figure out if we have cycles in any of the smaller graphs that are like intra-group graphs. And if we don't have cycles in either of those graphs, we will be able to run a topological sort, starting with a number we can start in the number that has the smallest in degree out of all the points that the group that has the smallest in degree. And this graph also doesn't have to be connected, so there can be several subgraphs. And then we start with the group, and we know all the elements that belong to this group, and we just do ordering inside this group for those elements. So we have like a subgraph for the group. We do the ordering of the subgraph, running the topological sort again from the smallest item, like the item with the smallest with 0 in degree, basically. Okay, and yeah, that's it. We do topological sorts for all graphs, one after the other. And if we have several options for the current group, we can choose either of those. And that would solve our problem. So what would be the solution? Runtime and complexity, space complexity. Let's see. Solution runtime. So we are creating the graphs. So there are like these are the edges, before items are the edges, and the items will be both n and m. So for creating those graphs, we will have, let's say, total edges equals k. So it will be O of k algorithm. K plus m plus n, because it might be that we have more groups than edges or more items than edges, and then these two numbers might dominate. So it will be O of k plus m plus n algorithm. Runtime. Now about the space, again, k plus m plus n, I'm guessing. Yeah. So now I will start with a pseudocode, right? So we will have a function that like does topological sort for a graph and outpost list of them. Okay, list of integers. I wanted to use it both on the group and item level, but fortunately we have IDs both for groups and items. It's just that we will also need to create a reverse dictionary that points from... Oh, we already have... No, we don't have. We need to have a reverse dictionary that has group and points to the set of items that belong to this group. So topological sort of the graph, and it produces the list of integers. So then what we do is we also need to detect cycles of graph, and it returns a Boolean value. Then we will like create graphs. So group graph and m item graphs, and these don't have to be connected. This also don't have to be connected. And then we will run this like detect cycles on each of those. So this will be detect cycles will be of m plus n runtime, and topological sort will be also of m plus n runtime. And we just need to always pass the same things here. That will be just abstracted graphs here between group IDs, here between item IDs. And once we apply this, so first we will be applying topological, we will be applying detecting cycles. So if any of the graphs has cycles in them, then we will be just outputting that it's impossible to create a solution, so an empty list. And maybe let me create okay, so all three items, let's say they belong to the same group or they belong to different groups, doesn't matter. So let's say it's this. Oh yeah, there will also be this issue with the items that don't belong to any group. Can we just treat those items as a separate group? I don't think so. It's essentially like each of those will belong to a group of its own. So we will need to create groups for them. So also we will be like adding add groups of their own for non-group items. And that would finalize our approach. But here I was just trying to do this, right? So show an example of, let's say here, the first item should come before it, and here, or like, let's say second item here, and for the 0th item here, and first item here, and however many items we have. So we have spent 20 minutes. Let's spend more time. So here we have a cycle because all of these are pointing to each other and we cannot create it. So we have n is equal to 3 and m is equal to 1 actually, right? And then we are returning an empty list just because there is no option that passes the whole thing. And it doesn't matter where we have them in groups or not. Okay, so implementation. So first of all, we will create all groups, which will be equal to group copy. I just don't want to modify the input in place. That's a bad practice. So then for I in range length, or we just have n, right? If all groups I is equal to -1, let's just call it all groups I is equal to m plus or equals to 1. So we will be manually increasing the number of groups, but just so that we can process all of those independent items independently. They had to complicate the problem even further. Couldn't they just create a problem where each item should belong to its own group? No, they also have to create like this corner keys. Fine. I digress. Now let's define our functions. So we have topological sort of graph, and graph will be a dictionary that points integer to list of integers, and it returns a list of integers. Pass. Oh yeah, I shouldn't probably not be forgetting self here. So this is topological sort. Then we also have detect cycles. And just to be clear, yeah, probably there is some way to do a topological sort while also detecting cycles. But first of all, we are not trying to optimize for elegancy of the code. We are optimizing the complexity, and the complexity won't change. Secondly, for anyone who is reading this code, it will be easier. But yeah, if that was a function that had a lot of load, so we need to increase throughput, then we would basically try to improve this algorithm. For now, I don't think this is a good idea. We'll just treat those problems separately, and also detecting cycles and doing topological sort are general problems in graphs, so we can even like reuse some functions here. And I actually won't be even implementing this right now because I don't want to go into these details. I first want to to create my graphs and then finish this like overall function. And afterwards, I will be focusing on those particular general functions. Okay, so now we have all groups. And now we also need to create a group graph. So group graph will be equal default dict of list, and then for group ID in all groups. And I also need an item number, so enumerate all groups. Just notice that we haven't changed the size of all groups. It's still the same size, so there's still the same amount of items. It's just that we have assigned items to groups of their own. So we are now creating group graph of group ID, append I. Okay, so they will also be ordered, but I don't know if that matters. Probably not. Then what do we need to do afterwards? So we need to figure out for the group level if we have, no, it's actually not a group graph, right? The thing is that we'll have to, like, this is group ownership, right? So basically group pointing to specific items, but then there will also be another group graph. So let's call it differently. Let's call group, I forgot who this word, but let's ship. So that's just this. I see that there is a message on the chat, so let me see what's there. Okay, chats. Hey, Odyssey. I guess it's Odyssey. Fact Odyssey. Nice to meet you. Let's continue. So this is just group ownership. Now we need to create group level graph, which is the most complicated thing. So we will need to create edges between groups if they don't exist. So here we are passing this as list of integers. It can be a set of integers, doesn't matter. So let me just modify it after the fact. The thing is that between groups there can exist several relationships, so several pointers. And if we find that there is a cycle like back and forth between two groups, we can just return an empty list right away. So how are we going to process this? So what we have is before items for item in range length of before items. So before items, okay, in range n. For before item in before items item. So this creates a graph for us, a graph path for us. So we do a group graph that will be default dict of set. Oh, I am calling this incorrectly. Set. And now for this group graph, we will be doing what? So if item in group graph before item, return empty list. So that's basically, it means that we are trying to add a new edge, but we also have a reverse edge between the groups. Yeah, no luck this scenario. But oh no, no. This is not the before item. We need to find the group for before item. So all groups before item. So we first find the group for this before item. And then here we also need to check that there is an all groups of the item. Okay, so otherwise, let me actually reframe this. I think it's not readable. So source group will be all groups item. Destination group will be all groups before item. So if source group in this destination group, then we return that. Otherwise, we haven't returned anything, so we are fine with creating this graph. I'll continue creating this graph. So group graph will be of source group add destination group. Okay, so we have created group graph. Now let's create all the item graphs. I think we actually need to do it a little bit differently. So side group graphs will be default of set for in range M. So we have created all the intro groups, and I think we don't need that, to be honest. I will just comment it out. Oops, I couldn't comment it for whatever reason, because yeah, I think I need to choose language first, but doesn't matter. I will remove it later if I'm correct and I actually don't need it. So here we will need to discern between two cases. So if belong to the same group, and in this and these other scenarios belong to different groups. So if they belong to the same group, then we need group graph. Okay. How to name this variable correctly? Intergroup graph will be equal to inside, let's call it just inside group graph of let's actually do it here. If source group equal to destination group, then we are processing this, else we're processing this graph, for example, source group. Okay, and now there in this inside group graph, we need to just add if inside group graph, and for we are now marking that item, and there should be before item, and for before item in return the same thing, return an empty list. Otherwise, we say that item is before item. Yeah, I know that it doesn't improve our running time complexity, but it simplifies thinking about the code, and I think it's necessary for the algorithm to work correctly. We will probably, like, running topological sort will also be able to process those cases when we are going back and forth between the two items. But since we just can remove those cases right away, let's just remove those cases right away so that we have more standardized graphs to worry about. Okay. So far, so good. So we have created all our graphs. Now, for if self detect cycles of group graph, return empty list. For inside group graph, inside group graphs, if self detect cycles of inside group graph, return an empty list. Now yeah, now group ordering will be self topological sort of group graph, and now answer will be an empty list. And then for again, okay, no, actually not that. For group in group ordering graph, let's for consistency call it this, single graphs of group. So we are choosing the specific graph that should go in this particular place, and now we need to do internal ordering of this graph. So we run items will be, or let's call it sorted items, will be self topological sort of this inside group graph, and then answer extend sorted items, and that's it. That's the core of the algorithm. Now we just need to implement topological sort and detect cycles, and then it should be the whole algorithm, if I'm not missing anything. That is, since we have already spent, what, 39 minutes, let me just try to figure out those two problems, right? Like topological sort and detecting cycles. Those are the general problems, but I haven't solved those in some time. So let's start with detecting cycles. Let's say we have a simple graph like 1, pointing to 2, and then here 0 pointing to 1, and then basically I don't know how to draw that, but you get the idea. Maybe I should do so 2 is pointing back to 0. So how do we detect the cycle? We can start yeah, we can start DFS from any node, and we will be recording a parent. So we will be recording parents for all of those. So for any step like for this, we will be checking what is the parent from which we visit this node. And here we start with itself. And then we can check like, so here we start with the parent. We say that the parent is like -1. And then whenever we come to a new node, we check whether we are coming from the same parent or from a different one. If we are coming from a different parent, that means that we have traversed the graph and found a new way to get back to our current node in the graph. And that would mean that we have a cycle. Let's check our assumption. Let's say we have a different situation. Let's say that we have a situation like this, right? So now the parent of -1 will be 0 will be -1. Here it will be 0. And for example, 2, it will be 0. No, it doesn't work, right? If we do DFS. Okay, I need to repeat the algorithm for detecting cycles. Maybe we need to store all the nodes that we have seen so far on the path. So if we are traversing from here and we are storing those nodes, yeah, we basically, yes, this would detect the cycles. We are storing all the nodes while we are traversing the graph in a set, let's say. And then when we exhausted some branch, we just backtrack and remove those nodes from the graph. But if we encounter a node that we have already in our like explored path, that means that we got back to one of the nodes on the path that we already explored, and that means that there is a cycle in the graph. Okay, so detecting cycles done. Topological sort. So now we know that like the relations between different graphs. Oh yeah, there is also this issue that in my topological sort, I was in my graphs, I think I can just order. Okay, I will need to reverse the list in this topological sort when I'm returning so that this algorithm is correct. But let's say we have this situation, right? How do we sort this topologically? We only know the in degree and out degree of the nodes, right? So we can calculate which nodes have the smallest in degree. And it can be actually several nodes. So let's say we also have something like 3 here. So node 0 and node 3 will have the smallest in degree, like the in degree of 0. We will definitely have such nodes if we don't have cycles. So then we start with any of those, and we start DFS. Oh no, actually. We need to instead do the nodes with the biggest n degree first. the nodes that have 0 out degree, right? Because they will be definitely at the end of our, yeah, there is no requirement for them to be after any of the other nodes. So we start basically with 2 that has no out degrees, 0 out degree. And then we basically, yeah, we remove those edges and we update our, update the graph and update the degrees of this. So we basically say, okay, now we have removed, like, the 2 is at the beginning of the graph, and we are saying that 2 is put there. Now we are removing edges from 1, from 0, and from 3. And now both 1 and 3 have also 0 out, have the biggest integrity. And no, okay, not biggest integrity, have no out degree. And then we are adding those in either order. And then finally we remove those 2 edges and we are just left with 0, and that will be it. So we will order, for example, 2, 1, 3, 0. And then we can return this, and this will be correct. Okay, so topological sort was also done. And once we implemented both topological sort and detecting cycles, we are done with this whole problem. Congratulations to us, 2400, unless I have made some stupid mistakes, which I definitely could have done. But thanks to, okay, I just need to stop sharing. Thanks to you, whoever was watching this, and see you in the next one. Bye.